Yeah, and thanks a lot for mentioning the C2QA, or the Co-Design Center for Quantum Advantage. To be honest, this is one of the things that's started getting me really excited about co-design, and not just because they're paying my bills, but also because of the fact that co-design really opens up some new opportunities for us to think more broadly, not just about algorithms, but also about hardware and quantum error correction. And the idea behind it is asking ourselves the question of how we can end up building virtuous cycles in order to be able to adapt our algorithms, in order to be able to meet the needs of and limitations of the hardware, but at the same time, look for opportunities for advantage, for particular paradigms that we frequently end up seeing in algorithms. And one of the big ones that I'm going to be trying to convince you of is that this idea of block encoding matrices is a really important idea, and coming up with good ways of designing our hardware and error correction, as well as even architectural concepts in order to reinforce this idea, I think is an important path forward for co-design and also quantum architectures. But we'll see if I'm able to convince you by the end of the talk about this. So to get to the main point of the technical kind of parts of my talk, we'll be talking about quantum simulation and the way that co-design can potentially give you advantages for quantum simulation. And as always, if we take a look back in history, right, the computation has always really been a significant driver of our physical understanding, going all the way back to the Antikythera device, which is one of the earliest known mechanical computers, which was used actually arguably as an educational tool to be able to help people understand what the motion of planets will be. And these simple simulators, of course, have adapted through leaps and bounds, going all the way up to large-scale data centers, as well as the clusters that we use, for example, to do device modeling for the detectors at the Atlas detectors at CERN for the LHC. So the scale of the computation is vastly greater, but at the end of the idea, the whole idea behind all of this is that, if we've got the world, like, this is clearly the world. Oh my God, my art is so bad. Okay, the idea basically is to take aspects of the world and model them inside the computer. Now, the core idea behind quantum computing and quantum simulation really asks, okay, is this feasible to be able to simulate all of reality inside existing computers? And the answer that we've increasingly come up with to this question is probably not. Not because it's intrinsically impossible. In principle, a large enough Turing machine can do just about anything that we can conceive of, well, except the halting problem and compute uncomputable things. But in any case, we believe it can simulate any physical process, but not necessarily in polynomial time. So the real question is, well, what type of a computer would we need in order to not just be able to simulate, say, the detector, but also be able to simulate a complicated physics that's happening inside the collider, or future colliders for that matter? This actually raises the opposite question, which for me is the more fascinating one, and the one that drew me into quantum simulation in the first place. The question is, well, really, what if we view the universe as a computational device? What would its power be? And how can we leverage the inherent computational power of the universe? So, from my perspective, this kind of question is really something that I think has been most fully explored by Minecraft players, ironically. So if you take a look at the early days of Minecraft, a game which I've spent far too long playing, the earliest computers that were built using it were built using a subtle bug that ended up happening with minecarts. So in Minecraft, what you have is you've got minecarts that are capable of going up and down rails. Now, when they were written, there was actually a bug in the collision detection algorithm to determine where the outside of the bounding box lies for minecarts. And it turned out that these bounding boxes stretched beyond the width of a rail that the minecarts were going down. And this bug allowed crafty players to realize, oh, wait a second, if we've got two minecarts that happen to be going down simultaneously on two different rails, they can interact with each other and collide. And given the buggy physics that they ended up having for this, this would actually cause the two to scatter away with larger energy. In short, by doing this, we could actually end up creating AND gates just using minecarts. And so then the idea was, well, you can use these operations and the kind of janky physics of minecarts in order to be able to do an arbitrary computation inside Minecraft. So the basic gist of what we typically do in these video games is we look for weird rules and find ways of exploiting this to get some kind of a computational advantage for tasks that we wouldn't be able to do. At some level, we can think of physics the exact same way. Physics gives us these kind of janky rules of quantum mechanics. The question is, what computational power do these laws represent? And in turn, what can we do with them? And that's the main goal of quantum simulation, is to be able to quantify what the computational power of physical processes are. And so that allows us to be able to do a host of different things and get advantages, albeit in some cases polynomial, in some cases exponential, for solving problems. For example, a polynomial one that we could end up taking a look at would be this traveling salesman problem, but of course we can't get an exponential speed up for that one. And further, we can end up taking advantage of properties such as interference between quantum systems in order to be able to do things that we really wouldn't be able to do otherwise. So this is the key idea behind it. And co-design essentially is saying, all right, well, if there are particular advantages raised by physics in a device, then we should try to look for ways that our algorithms can exploit this. And similarly, actually, it's not really just hardware that we should be considering for this. The reason why I bring this up is because if we take a look at the software stack that we're ultimately going to be using for this, the algorithm that we're looking at will likely have to run on top of some kind of a quantum error correcting code. And this will have to sit on top of a physical hardware. Or physical qubits, which itself are an abstraction for the quantum control that's going down at a lower level beneath this. And the key thing is that if we know we've got an algorithm, what we should be doing is we should be finding the right quantum error correcting codes to meet the needs of the algorithm, because the interface to the algorithm is actually through the quantum error correcting code rather than through the physical qubits in this case. And we should tailor that in order to fit the algorithm, not just the physical layer in order to fit the algorithm. So we need to, if we want to squeeze as much as we can out of these systems, we need to be able to build all of them together and find a way of, instead of thinking about it like people like me had in the past, of just getting our gates good enough so that quantum error correction can solve absolutely everything and sledgehammering the entire problem. Really, we should ask ourselves, how can we best optimize all of the relationships between these in order to solve our problems? And that's the whole idea of co-design. And one of my big claims for this talk is that we should really be thinking about co-designing hardware in order to enshrine the notion of block encodings. And actually, this isn't as strange as it might seem. One of the reasons why this isn't so strange, and this is an example of work that I've done with Steve Gervin, as well as others at Yale and Pacific Northwest National Labs. The basic idea behind this is to take a look at building a programming language, or I should say, building an extension to Qiskit that really enshrines this notion of qubits interacting with bosons. Now, this is important because if you consider circuit QED, what you have in these cases is you've got a cavity that has a number of different photon modes inside of it. Now, inside the cavity, there's individual qubits, and the qubits can be tuned resonantly with the photon modes, which allows you to actually manipulate and interact very strongly because of the cavity with the individual microwave photons that are going on inside the cavity. And this leads to these sorts of bizarre circuits over here, where we have this notion of a qubit and a Q mode at the same time. The mode is really just the mode for the photon that's inside there. And what we can do is we can end up performing things like displacements on the mode controlled on the value of the qubit going inside. So this is sort of a hybrid model of computing where we have ordinary qubits like we all know and love, but at the same time, they're interacting with photons. And so this is a continuous gate set in this abstraction over here. This over here is universal, and it gives us access to an enormous Hilbert space inside the degree of freedom of the photon. Specifically, what we have, at least in theory, we have an infinite dimensional Hilbert space that we can deal with, and we can do things like displace the modes inside the cavity controlled upon the qubit. So down below over here, this is an example of preparing what's a so-called Schrodinger cat state out of in this system, and it involves just basically by doing something like the following: you prepare a qubit in 0, you apply a Hadamard to the qubit, then controlled in the value of the qubit, you perform a displacement of the oscillator, either forward or backwards in alpha. So these two are displaced in alpha over here. And then we measure at the top. And these Wigner functions over here will give us a quasi-probability distribution for the different parts of the wave function when we take a look at it. And we can see clear signs of interference showing that this is actually a genuine quantum state that we end up getting out of it. But the key thing is that we've got photons and qubits talking to each other. So the question is, well, what can we do with this? The first thing that we can do with this is actually really kind of neat, because this qubit up here will, depending on whether the value is 0 or 1, it will perform a displacement of alpha up here and a displacement of minus alpha down here, and it will do nothing up there. So if this is our unitary, we can actually view this unitary as representing the displacement operator that we're looking at inside a block of the larger matrix. So actually, as I'm going to explain later in more detail, this hardware itself natively has what we refer to now in quantum simulation as a block encoding. And we can use the full power of quantum techniques to manipulate this and do things that would be astounding if we only had the techniques of, say, 5 years ago in order to be able to manipulate this. The next thing that, of course, we get access to is we have photons. So if we want to simulate, say, a photonic system, it makes a lot more sense that we would get advantages by simulating it using native bosonic hardware rather than having to emulate bosonic operations using qubit hardware. And to give you an idea about this, let's take a look at the simulating a James-Cummings model. So I don't want to take too big of a distraction and jump into the physics of the James-Cummings model, but the key problem that we end up having for simulating this model is that it basically ends up involving bosonic creation and annihilation operators. And here's a sum of a bosonic creation and annihilation operator, which is one of the common terms that you'll end up seeing in these things. Key thing about it is that you'll notice these pesky square roots that we get over here. Now, if we want to be able to simulate this on a quantum computer, the easiest way of doing it is to decompose these matrices into sums of what are known as two-sparse matrices, like these ones over here, which are direct sums of irreducible two-dimensional blocks. Okay, and each of these irreducible two-dimensional blocks has these square roots in it. So if we wanted to be able to simulate this on a quantum computer, the standard way that we would have to go about doing this is computing square roots. Now, computing square roots doesn't sound so bad, right? Like your calculator computes square roots, no problem. But the problem is that if you're using a reversible circuit to be able to compute square roots, every time that you do a multiplication, if you want to do something like ket x times ket y, this is an irreversible operation. And so because it's irreversible, we can't map this to x times y. Instead, we have to map it to x times y using a Bennett trick. And further, if we want no loss of precision, the number of bits that we need for the product, if this has to be double the number of bits that we have for the input. So every time that we go through and do a multiplication, we need a ton of extra ancilla bits. And in practice, if we take a look at what we would need to do these types of calculations, it's common that using techniques like Newton iteration to be able to solve this will require thousands of qubits just to evaluate the square roots that are coming in here. And further, a ton of 2-qubit operations. So if we take a look at the cost of of a simulation down here, this is just a single Trotter step as a function of the number of qubits that we're considering for our cutoffs for these harmonic oscillators. We end up seeing that actually, even the cost of doing this square root operation, which is the biggest contributor, ends up giving us something for even 100 qubits. About 10,000 gate operations will be needed in order to be able to do just a simple Trotter step of this Hamiltonian. Whereas the actual bosonic simulation circuit, if we had access to these native operations that the hybrid hardware that I discussed previously have, then under those circumstances, actually, we only would need a constant number of operations inside that model in order to be able to do this. So that's the total number of gate operations. There's this green line down the bottom. Now, of course, there's issues about how to error correct this gate set that are still open. But I wanted to bring this up as a successful example of a case where where you can take advantage of the properties of a particular gate set that the hardware is afforded and find applications that are radically better because they do a better job of matching the hardware than bending over backwards and doing it with qubit supports. So this is one of the things that I think is really exciting about the perspective of co-design, that we can achieve, in some cases, factors of thousands speed up relative to the best methods that we currently know for doing things using a traditional algorithmic approach. So to go forward, though, I didn't really discuss too much about quantum dynamics or the notion of block encodings, and it wouldn't be one of my slide decks unless you saw a variant of this slide. So those of you who've seen me speak a bunch, I apologize. You can check your email now. But in any case, the basic idea of what we want to do with Hamiltonian simulation is we want to be able to compile a unitary that describes the time evolution into a sequence of elementary gates. Now, conceptually, the most straightforward way of doing this is simply to take the time evolution operator, e to the minus iht, and write that as a sum of a Taylor series up to some finite order for the Hamiltonian. Then the idea would be if we can actually implement this sum on a quantum computer in some way, then we would be able to carry this out. And so the key approach that's used for this, or the key way of thinking about this at a high level, is that with quantum simulation, the central problem is you begin with a quantum state up here whose dynamics you'd like to simulate for some mathematical description of a physical system that you would like to simulate. Now that state needs to be encoded as a qubit string inside your quantum computer. The entire simulation takes place in the quantum computer, but we need these mappings back and forth between the physical system and a subspace of the quantum computer in order to be able to make the simulation make any sense. So the physical system undergoes some continuous time evolution from its initial state to its final state. And we'd like to mimic that. And the way we mimic that is we take the encoding of the initial state and we carry through a series of discrete gate operations to map that forward to a final state. And this final state at the end is one that we promise is going to be back to be logically equivalent to a state in the physical system that is epsilon far away from the actual true state. So that's the idea. Everything in principle with quantum simulation actually is all about these mappings. And we are demanding for the dynamics that we have a promise that the error in this simulation is small. So obviously much of the work inside quantum simulation goes into rigorously proving that when you do all of this, you get epsilon error coming back out. Now, the question is, how do you carry out this, this process of summing the Taylor series that I drew up above? The simple way of doing this is to use this method that is descriptively called a linear combination of unitaries, or LCU. And the basic idea is what it does is it gives you a way of implementing a sum of unitaries as a subblock of a larger matrix. And this is what we now refer to in the algorithms literature as a block encoding. And this concept of a block encoding has really opened up a ton of new horizons in algorithm design because it allows us to do a bunch of things that we wouldn't be able to do. And so in particular, let's imagine that what we have is we want to be able to implement the sum of two unitaries, U and V. We say that a matrix, U plus blah, 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 down over here, block encodes the sum of the unitaries if there exists some constant alpha such that the sum of the unitaries divided by this normalization constant is a block of the larger unitary that we need to build. So that's what we mean by block encoding. It means that we take our matrix, our matrix that we want to build, and we just stick it inside a block of a larger unitary matrix. Now, the sum of unitaries, interestingly enough, doesn't actually need to be unitary. Let me give you an example to show you this. One of my favorite examples is I plus Z divided by 2. Both of these guys are totally unitary. But when you sum them together, you get 1/2 plus 1/2 minus 1/2, which is the exact same thing as the projector onto 0. So actually, if you do the linear combination of unitaries trick, and spoiler alert, I'll show you what you do for that here. It is really actually just this circuit. If you perform this particular circuit on a state psi, conditioned upon you measuring 0 up here, this block encoding will apply identity plus Z over 2, which is the projector onto 0. So if you measure this top qubit to be 0, then psi will get mapped to 0, 0, psi. Okay, which in other words is equivalent to us measuring the bottom qubit by measuring the top. So this gives us a way of thinking about how to do tons of non-unitary operations and implement POVMs by thinking about the outcomes that we end up wanting for the operation as blocks inside a larger unitary. But like the TLDR, I guess, for this entire approach is that you don't need, if you've got the ability to sum unitaries, you can actually build any matrix you feel like. And so block encodings really, actually, for the first time, give us the clear freedom to be able to apply any matrix we feel like, up to a normalization constant and some probability of failure to a quantum state. And that's why it's so powerful, because it finally gives us a way of escaping from the shackles of unitarity in order to be able to do anything that's permitted by linear algebra with some success probability. Of course, the art comes down to improving the success probability and the rest of it, but this is the core idea behind it. And so in general, if we wanted to take a look at, uniformly adding together 2 to the m matrices, a simple circuit that would end up constructing the block encoding for a uniform superposition or uniform mixture of all of these would be this up here. And you'll notice that actually it all has this exact same structure. We've got this control register up at the top that ends up representing which unitary we want to fire or add up in the sum. And then we have these guys over here, the Hadamards, which in some sense tell us the weights that we want for the individual terms. Here, it's the Hadamard transform, so we're picking the weights to be even. So there's no bias between what the strength of U1 or U0 is in the particular sum. All of them are equal. But the more broad way of thinking about this is that we call this circuit template that we use for LCU prepare, select, and prepare, where prepare creates the weights, select fires a particular unitary, and when we combine these things together, we can use it in order to be able to implement an arbitrary sum of unitaries. Of course, an arbitrary sum of unitaries can be used to make an arbitrary matrix. And that point may not be obvious to you, but it actually is, because the poly group is a orthonormal operator basis. And so every matrix can always be expressed is a sum of poly operators. And because poly operators are unitary, this ends up meaning that, well, every square matrix, at the very least, can always be written as a sum of poly operators. And thus, this circuit template is capable of block encoding an arbitrary matrix. So that's how the whole thing ends up going. Now, specifically, the way that we can end up addressing this is by doing the following. We can consider building a prep circuit that ends up, say, taking a Hamiltonian that more generally is of the form sum over j alpha j of t, because we could consider the time-dependent case, uj over here. The most generic way that we can end up doing this is by coming up with a circuit that encodes all of these amplitudes for our prep. And so the basic idea behind this is that what we do for the time-dependent case of the exact same thing is we create a prepare circuit that will prepare a sum over the square roots of the amplitudes evaluated at each of the times for these coefficients. And so it takes this, what this prep circuit does is it takes an individual time in here and does the following. And then we just need to, if we want to handle the time-dependent case, we need to create an appropriate weight over the times in order to be able to simulate the quantum dynamics. And the select operation does exactly the same thing it does in the time-independent case. It will take an index corresponding to the particular unitary that you want to include in your superposition. And given that register corresponds to the index, it will apply the corresponding unitary to our state. So these are the two operations that go into handling the time-dependent case. Now, the way that we deal with the time-dependent case is we can't use a Taylor series expansion to look at the time evolution operator, or at least we shouldn't use a Taylor series expansion because there's nasty derivatives and stuff like that. The better way of thinking about it, writing this as a sum of unitaries, and in turn, writing a block encoding for the time evolution operator, is to use what's called a truncated Dyson series. So the Dyson series gives the following integral expression that ends up closely approximating the time evolution operator when you truncate it. And the truncation error for truncating it at order k shrinks really quickly. It goes like 1 over k factorial. So for k equals 10, you're probably pretty good for just about everything, because 1 over 10 factorial is like tiny. And in general, you end up getting some scaling that goes like log 1 over epsilon divided by log 1 over epsilon, if you want the truncation error to be epsilon, after using some Stirling's approximations and stuff like that. But one of the things that's really kind of neat about this approach is that when you go through and do all of this, we end up finding that we can implement this formula using a number of queries that are actually independent of the size of the derivatives. And that actually is a really kind of shocking observation that was made relatively recently. And what this ends up meaning is that actually quantum simulation for time-dependent Hamiltonians doesn't depend on how quickly the time-dependent Hamiltonian changes. It actually just depends on how big the Hamiltonian is. And so just to give you an idea about what this ends up looking like, this is the form of the circuit for simulating a time-dependent Hamiltonian, or the most broad family of Hamiltonians that we know how to simulate using this linear combination of unitaries approach. But the fact that we have the ability to perform the simulation using a number of queries that's independent of the size of the derivatives, this actually opens up a new possibility for us. And the idea basically is that what we can do is we can do something like the following. If we've got H equals H big plus H small, what we can do is we can go into an interaction frame of this where we transform to the rotating frame of H big t, H small, e to the I, H big t. And once we end up doing this, the magnitude of the Hamiltonian the magnitude of the Hamiltonian is actually just the norm of H small, not the big part. And because the cost of the simulation depends on the integrals, not the derivatives of the Hamiltonian, these massive derivatives that we get from this ridiculous rate of spiraling from the H big at the top doesn't affect the complexity. And so what this allows us to do is take advantage of structures inside the particular problem. If we have terms that are really big, we can use this approach in order to be able to do cheap simulation. And this is one of the reasons why actually often what we'll do is we'll have a time-independent simulation. We'll actually map it to a time-dependent simulation using this interaction picture idea to reduce the cost. And at present, the best known scalings that we have for time-dependent simulation come from doing this trick. And so more broadly, I guess I should say, there's an appreciation that time-dependent simulation isn't just a curiosity. It's actually a really powerful technique that we can use in order to be able to simulate systems that are time independent, because of the fact that we can use these frame transforms to reduce the cost. So that's a new realization, and it's been used in a big way recently. But another opportunity that ends up coming up that we can take advantage of using these types of systems that have ancilla controlled operations, just like the hybrid bosonic qubit systems that I was talking in the past, is this idea called the quantum singular value transformation. The basic way that, or what this allows us to do is it says, okay, let's say we've got a matrix A that we've block encoded using a linear combination of unitaries. One of the things we'd like to be able to do is we'd like to be able to not just take A, we'd like to compute F of A. So we'd like to be able to do something like do one of them square roots, and hopefully in a cheap way that doesn't require a ton of qubits. The nice thing about this approach is it allows us to compute any arbitrary, well, okay, any mostly arbitrary, it's an even or an odd polynomial function that have some relatively loose restrictions on it. But barring that, we can implement such functions actually using this technique directly on a quantum computer, and we only need, worst case scenario, 2 extra qubits to be able to carry this out, rather than the thousands that we ended up needing using some of the reversible circuit techniques that we used earlier, or that were used earlier. And the basic idea behind this is that, as I said before, what we do is we build a unitary that block encodes the matrix that we want to transform. And in this case, I'm assuming for simplicity that the matrix A here is positive semi-definite. So what we'd like to do is we'd like to take that matrix A, which is block encoded here, and we'd like to construct an even bigger block encoding such that the function of A is encoded in that block at the top. And that's what the quantum singular value transformation does. It gives you a prescription for carrying this out. And so if we wanted to do something like a matrix inversion, the function that we'd be taking a look at would be A inverse, which we can easily approximate by, say, an odd polynomial. And I should mention recently, there's a beautiful paper, if you're interested in this idea that Ike Schwang and his students ended up writing, called A Grand Unification of Quantum Algorithms, that gives a excellent review and a few new applications of this idea. And I strongly recommend those of you who are interested in this, take a look at it. But the moral of the story is that block encodings give you a way of building a matrix A inside a block of a larger unitary matrix. The singular value transformation allows you to compute a function of A as a new block encoding inside that matrix. So with these two things together, we have an entire linear algebraic toolbox that we can bring to bear against problems. And it makes a whole bunch of things vastly easier conceptually than they were in the past. And so just to give you an idea about what the quantum singular value transformation ends up looking like, it basically ends up looking like this. If we want to, U over here is the unitary that block encodes the matrix that we'd like to transform. The rest of it, in order to implement the function is just specified by these rotation angles that are carried out on the qubit at the top. And there's an efficient algorithm for computing these rotation angles. And there's some great work by Junwong Ha as well as Lin that you can take a look at to give you nice algorithms for computing the phis that you would need in this to implement the function of your choosing. But every single time, the circuit ends up taking this exact same paradigm. It switches between rounds of U inverse, with these phase modulations on an extra qubit on the top. And by choosing those phase modulations, you can build any even or odd modulus and sensible restrictions polynomial you want. So to give you an idea about what this would look like for the problem of doing the matrix inverse, which essentially is the HHL problem, is what we do is we would say, okay, well, let's promise that the condition number of the matrix is bounded inside this regime over here. What we do is we build an approximate polynomial that mimics 1 over x outside of this region. And inside here, well, we make no promises about how well it performs. And so basically, that's it. We just build this polynomial, we let it rip, and that's how HHL ends up working in this. And it's nice because there's no phase estimation. There's a truly tiny number of qubits that are needed. And yeah, it's a straightforward application of this whole block encoding idea. Another beautiful thing that you can end up doing with this approach is things like a threshold function. So we can do something like, say, take a, with QSP or quantum signal processing, we can do something like take an RZ of A gate coming in over here, and then apply a threshold function to the value of A. So in this case, we could end up doing something like, we could map it to RZ of pi by 2 if A is greater than delta and RZ of 0 otherwise. And this essentially is how you can implement fixed point amplitude amplification in this approach. We just do this threshold transformation on the rotation angle. And this notion of the quantum singular value transformation and quantum signal processing give us this way of doing it. Similarly, linear amplification or de-amplification gives us a way of doing fractional queries really easily in this. So this framework really does live up to Ike's hype, I think, because it does give you a beautiful way of implementing all sorts of amazing things. And as a result, because this gives so many things, I really believe that this should be thought of as a primary target for co-design, because by building hardware, error correcting codes and the like that end up facilitating this application, we end up getting a ton of things that we can do as a direct result of this, this one simple algorithmic primitive. Okay. And so, as I said before, the basic idea behind simulating quantum dynamics with the truncated Taylor series method is that what we want to be able to do is we want to just be able to block encode this e to the minus IHT. However, a more natural way of doing it is to do it using this cubitization approach, which was pioneered a few years back. And this gives a way of block encoding a Hamiltonian divided by alpha. Or another way of looking at it is it essentially block encodes a two-dimensional rotation inside an irreducible vector space spanned by each eigenvector and a isometric extension, as well as its conjugate with this circuit at the top over here. But at high level, it kind of is something like this. It does something like arc sine of h over alpha. Actually, it's more naturally arc cosine, but the two are kind of almost the same function. So the moral of the story is that what we have is we have the ability to be able to carry out the arc cosine of the Hamiltonian. And this is really cool because this particular circuit is super simple and it has no approximations. So if you're used to Trotter or other methods that are approximate, cubitization is a breath of fresh air because there is literally no approximation that goes in. The biggest problem is that you don't get the eigenvalues back out you want. You get the arc cosines of the eigenvalues. But fortunately, using these techniques, what we can do is we can actually transform the arc cosine back to the ordinary function, because all we need to be able to do is do a transformation in the exponent where f of x is equal to cosine of x. Okay, so by doing that, we can invert the arc cosine and turn this into an ordinary Hamiltonian simulation method. And it technically requires a couple of steps in order to be able to carry out, like a Jacobi-Unger expansion, and then a linear combination of the odd and the even parts, because the technique can only do the odd or even polynomials. But spiritually, at a high level, that's really what goes on, and how this technique, this block encoding technique, can be used in order to turn this simple circuit over here, that's almost a simulation, into a bona fide simulation. And furthermore, it's provably query optimal too. So let me skip over all of this because I'm almost certainly running out of time. But the last thing that I kind of want to talk about that you can do with block encodings is this question about time-dependent simulation. So previously, we showed how you can build block encodings for space, in a sense. We can take a matrix, A, and crunch it into a block of a larger unitary in this form. But the question is it possible to also block encode time? So what I mean by that is that we have our truncated Dyson series, which says e to the minus IH t integral dt, and this is time ordered, is equal to identity minus I integral h of t dt. Hopefully my pen will catch up in time. Yes, it will. All right, cool. So we can use this series in order to be able to build the whole thing up. The question is, well, can we consider building a clock on the outside of the quantum system that will actually just keep track of the times and treat this entire dynamics actually as a time-independent problem? And we can view this also as a way of block encoding not just space, but also time. And so a way of taking a look at this is the following. What we do in our approach to block encode time is we consider making two spaces. One is the space of a clock that keeps track of the time the system is supposed to be applied at. And then we build a time-dependent Hamiltonian that looks up the time in the clock and then applies the correct Hamiltonian to the physical space. And we need to be able to make sure that the clock consistently evolves in time in a way that's independent, or at least approximately independent, of the evolution that we end up seeing in space. Because if the two end up getting entangled, then badness will start happening, and you'll end up having the speed that time progresses through it be different for different branches of the quantum simulation, which would be really, really awful. So that's ideally what we want to be able to do. We want to be able to come up with a time-independent Hamiltonian that actually is capable of mimicking the time-dependent dynamics in this way. And one way to think about this, it's non-rigorous, that was put forward in the literature years ago by Masuo Suzuki of the Trotter-Suzuki formulas, was to consider this time-ordered a time displacement operator. And the basic idea behind a time displacement operator is that if you sandwich it around the Hamiltonian, it'll evaluate the Hamiltonian at a later time. Now, you can see that if h of t is an analytic function, then it's got a Taylor series, and the only thing that we can end up getting from using the Hadamard's lemma to expand it all out and comparing it to the Taylor series, that the commutators of tau with the Hamiltonian have to be equal to its derivatives. So we can end up viewing the tau operation essentially as a derivative operator, which is great. Okay, so this builds a lot of intuition. We can put this tau term in the exponential in order to be able to deal with time displacements. And in turn, by going through a Trotter argument, we can argue that the Trotterized decomposition of e to the I tau t times e to the negative h plus tau, where tau is this operator above, this should actually correspond to the proper time evolution operator. So if we can build this derivative operator, which in some sense kind of acts on like a clock space, it would be able to carry it out. Problem is that all of this math is bullshit. I mean, apart from that, it's great, but this is entirely wrong. The reason why this is entirely wrong is because of the fact that the operator is a derivative operator is an unbounded norm. And furthermore, it's not even acting on a Hilbert space. So many of these expansions that we're carrying out aren't guaranteed to converge. And we need to really concern ourselves with whether or not this process even makes any sense. And so this is the whole idea of the block encoding approach that we ended up taking. What we do is we try to come up with a discrete version of this exact same idea. And well, okay, like Master Yoda once said, we did more than try, we did. So the way that we did this is we built two registers, a clock and the physical Hamiltonian. The clock Hamiltonian is really just designed in order to be able to do a discrete displacement. And the way that we kind of generalize the notion of the derivative is by a quantum Fourier transform conjugating this diagonal operator in the middle. So you can see this over here. It kind of looks like a discrete approximation to a derivative for that delta operator down at the bottom. So we build this and we use that in order to kind of naturally give the time some dynamics forward. And now the Hamiltonian we make dependent on the current time that the system's at. And this is the approach, and we can go through and be able to show that it carries out the correct evolution modulo these errors that can be made exponentially small by padding out our domain and increasing the number of bits of precision for our time. And these are the first two orders that we end up getting for our time evolution operator. So we can do this clock setup and block encode time as well as space with this approach. And furthermore, the number of times we need to be able to apply this in order to be able to carry out a total quantum simulation, basically with these lowest order approaches, scales with the second derivative of the Hamiltonian. And something that's really cool about this approach is that if we take a look at the case where the Hamiltonian is linear, then the second derivative correction doesn't occur. And we just have 1 times it. And this over here corresponds to the proven lower bound that we end up having for quantum simulation. So this, for the very first time, through thinking about these block encodings, gives us a time-dependent simulation algorithm that achieves optimal scaling. And before that, all the methods were near optimal. So this goes to show that block encoding time actually can be a really good thing. And it takes us one step closer to also being able to unify the ideas of qubitization, which don't work for time-dependent Hamiltonians, by finding a way of converting our time-dependent Hamiltonians to this block encoding of time, and thus allowing all known Hamiltonian simulation methods to simulate it near optimally. So that's one of the reasons why we kind of want to do it. Now, one of the things that I really kind of want to bring up about this, Okay, I've hammered home all of this as saying that blocks are cool. Okay, they really are. Block encodings really are the most flexible paradigm that we've come up with in quantum computing, and a host of ordinary algorithms, such as many quantum walk algorithms, for example, as well as Hamiltonian simulation and linear systems. Tons of things are direct consequence of these ideas. By using them, we end up getting ways of implementing linear algebra, like the matrix inversion problem that I showed, or Hamiltonian simulation vastly faster. And so because these are so important, it really is important to start taking a look at what co-design ends up meaning for block encodings. And it's my firm belief that we should begin exploring new architectures as well as new ways of thinking about quantum error correction that will make these types of block encodings easier. And in particular, look for ways where we can have ancilla controlled operations, like this pattern over here, easily implemented. And this not only creates great opportunities for algorithms, but also it's great for control. There are pulse sequences such as the BB190, that end up taking advantage of this exact same type of structure in order to be able to make your system vastly more robust to over rotation errors. And so by enshrining these ideas, we also open up the possibility of creating new potentials for control as well as algorithms. And it's my hope that by continuing to think about the architectures of these systems and optimizing them in order to be able to handle block encodings for both space and time, that we will be able to actually come up with quantum computers that can solve practical problems far earlier than we would be able to otherwise. Thank you very much.